Hi everyone. Today we're going to be talking about the fact that inverses in an associative binary operation are unique. Now this is quite a mouthful and I want to begin by getting the terminology right. So let's take a look at what these words mean. First of all, a binary operation. We'll remind ourselves of the fact that it's something like this. It's a function from a set with crossed by itself. It's a Cartesian product mapping to the set, and instead of using prefix notation like this, we're going to use infix notation like this. So we're going to put the function in between the two elements that it's operating on. Secondly, for this result, we're going to need the fact that the operation O has an identity. Let's call it E. If you haven't seen this before, what this means is that for all elements A in S, A composed with E is equal to E composed with A is equal to A. That's an identity, such as 0 in addition or 1 in multiplication. So far we've defined binary operation and what an identity is, but we're also going to need what associativity is. So a binary operation is associative if for all A, B, and C in S, A operation B operation C is equal to A operation B with this done first and then C. So we can switch the order of the way the operations are performed, but it stays the same. Philosophically, what the main implication of this is that we don't need parentheses when we have a sequence of these operations, but we're actually not going to need that fact. Now that we have associativity down, I want to talk about what inverses are. In fact, there are two types of inverses that come together to form general inverses. One of them, just like in functions, where we have left inverse of an element A and S. That's an element B such that B working with A is equal to the identity, and a right inverse of A in S is an element C such that A working with C is equal to E. So we've got these two kinds of inverses, and what we really want are general inverses of A and S. This is an element A inverse such that A inverse is both a left and a right inverse of A. This should be pretty reminiscent of inverses of functions, because there we also have left inverses and right inverses. Okay, now that we have the terminology down, let's get to the actual result that we want to prove. The theorem is that if a binary operation from S cross X, S to S, has an identity E, and the operation is associative, then any element that of S that has an inverse. Now note that not every element has to have an inverse, but if an element, let's say A, has an inverse, it has a unique inverse. So if there is an inverse of a particular element, it doesn't have more than one inverse, and we're going to prove that now. So suppose A is an element of S, E is an identity of the operation, and suppose A has a couple of inverses, B and C. Okay, so what we want to do at this point is show that B equals to C. And we're going to use associativity and the properties of inverses to do that. The idea is to look at B over A over C. We're going to compute this in two different ways. One is that B over A over C, the B over A is equal to E because B is the left inverse of A, and we get C, and that's just equal to C. And two, we're going to use associativity now. B over A over C, that's equal to B over E, and that's because C is a right inverse of A, so A over C is equal to E, and that's just equal to B. And when we combine these, we get that B equals to C due to associativity. So that completes the proof. Let me go back and review what we just did. We started off by reminding ourselves of what a binary operation is. We defined what an identity is. We just defined what associativity of a binary operation is. We defined left inverses, right inverses, and general inverses of elements of a binary operation that has an identity. Finally, we got to the theorem that we wanted to prove, which is that for binary operations that have an identity and are associative, any element that has an inverse has a unique inverse. And our proof depended on computing this expression in two different ways. One was in this way, and then using associativity in this way. And this allowed us to conclude that B equals to C. Okay, thank you for watching, and I'll see you next time.